So welcome back again. This is going to be part number 3 of collective communications. So we're going to basically continue from where we left off. So we talked about MPI gather, and we already discussed what is the semantics in intra-communicator scenario, and now we want to take a look at inter-communicator. So if communicator is an inter-communicator, then the call involves all MPI processes in the inter-communicator, but with one group, let's say group A, defining the root. All MPI processes in the other group, group B, pass the same value in argument root, which is the rank of the root in group A. The root passes the value MPI root. So this is exactly the same drill as what we had in broadcast, right? MPI broadcast or Bcast. All other MPI processes in group A pass the value of MPI proc_null as root. Data is gathered from all MPI processes in group B to the root. The send buffer arguments of the MPI processes in group B must be consistent with the receive buffer arguments of the root. Okay, so now let's just, so I'm rendering the other episodes. So Final Cut Pro is basically running in the background. It was called as MPI, what was the name? Gather inter, I think. Again, we're not going to comment on these stuff as we already mentioned the reason. Okay, here we don't have the case of like having an integer buffer and having C strings, but we only have a send buffer as integer, and then the receive buffer, again, it's going to be a null pointer. Then we find our way to find the root process in group A, and then we allocate the proper size for the buffer. Note that the proper size is not, again, sort of the size of the world size, but it's going to be sort of the difference between the two, which gives us the size of group B. Because in this case, gathering is basically going to be, let's say, collected in root process group A. So every process in group B is going to send information to process A, the root process of process A. So this means that this is the size of process, let's say this is the size of group B times the size of the integer. That's how much buffer we need to allocate with malloc. And then this is the drill about having MPI root send as the root process of group A, and then all the other processes in group A needs to send MPI proc_null, and all the processes in group B, they need to send the rank of root process in group A, which is 0. And then again, we call MPI gather, but this time in the context of inter-communicator, not in MPI com world. That's the difference. And then finally, this is group A, and the root process basically prints all the information that it got from group B processes. And since receive buffer is basically dynamically allocated with malloc inside root process of group A, again, root process of group A is responsible to free that resource. So let's take a look at this. MPI gather, and then inter, and MPI run. So you see that processes 4, 5, 6, and 7, they're in group B, and processes 0, 1, 2, and 3 are in group A. And this is a message from the root process number 0 in group A, which says gathered receive buffer from group B approx of these things. So as these processes are, let's say, in harmony with the rank number, because we have initialized where is it, our send buffer with the world rank. So that is why I exactly know that processes 4, 5, and 6, and 7 are in group B. That's the only reason. Okay, now we can move on. So the next thing on the line is actually gather V. The only difference that gather V has compared to gather is that it gives you, let's say, flexibility in terms of having your own counts as an array, Take a look at here. Receive counts is an array. And then it gives you also flexibility in terms of having different displacements. And these displacements, it's very important to know that these displacements are not in bytes, but it's actually in terms of how many counts of data that you want to have as a displacement. Again, the same drill goes here, that the receive buffer, receive count, displacements, and receive type are only significant at the root process because it's a gather operation. Only the root is going to receive the information from all the other processes. We say here don't need to allocate buffer for root proc. Allocated buffer size equals to the size of group B. Okay. See the example MPI gather V. That's basically the example we have. But before seeing the example, let's take a look at. So this is what you can imagine in your mind that is happening behind the scenes, but this is not exactly what is happening, but it says as if. So if the communicator is an intra-communicator, it means that the outcome is as if each process, including the root itself, sends a message to the root with a send buffer, send count, and send type, and the root, only the root, executes and receives, and these times the receives, they have custom displacements. That's beautiful, right? So this gives you a little bit extra flexibility. What is the semantics? Let's take a look at the semantics. The receive buffer is ignored for all non-root MPI processes. We already mentioned that. The type signature implied by send count send type on process I must be equal to the type signature implied by receive counts I receive type at the root. This implies that the amount of data sent must be equal to the amount of data that is received pairwise between each MPI process and the root. So let's take a look at this. Again, in-place option is available for inter-communicators as specified by passing MPI in place as the send buffer of the root. In such a case, send count and send type are ignored simply, and the contribution of the root to gathered vector is assumed to be already in the correct place in the receive buffer. So we're going to see the example right now. So it's going to be MPI gather v.c. So everything is going to be the same. Send buffer, receive buffer, and everything is going to be the same. Here, again, we add another level of complexity of sending strings as well. But the only difference compared to MPI gather is that we add these extra stuff. So we need to have displacements, and we need to have receive counts. These two are arrays. And we need to have a string displacements and receive a string counts. So these two are for the string, the C string, and these two are for the integer buffer that we want to pass. We want to basically pass around or gather it. And then in this case, the displacements are based on their ranks. So that is why we put this up until size, and then we initialize everything with the iterator inside this for loop. And then we have receive counts. In this case, we have everybody sending only one value. So that is why we have for receive counts an array of size with values of 1. Receive a string, again, is going to be 10. That is the counts, because our send string buffer is 10. And string displacements are going to be I times 10. So that is, again, based on their rank. So 10 is the size, and I is basically based on the rank. They're going to be different. Process number 0 is the only process that sanely we said is the only process that needs to allocate space for the receive buffer of the integer and the receive buffer of the string. So that is why we have size times size of integer, and then again size times 10 because of the size of this thing here, send string. And then we call MPI gather v, and the difference here is that in the call we only have this this receive counts as an array. This is not a single value, and we have displacements again as an array. Everything else is the same. I draw your attention to this one. This is an intra-communicator, so that's why we pass an MPI com world here. And in the case of sort of C string, what we want to do is basically we want to use MPI in place so that you see also how you can use MPI in place. And before using MPI in place, since the data is going to be read from the receive buffer, we are responsible to basically fill that buffer with the correct information of that string. And that string is already sort of allocated right here. So every process has its own version of this sender string, which is going to be hello followed by the rank of that process. And then finally, after we do the gather, so gather v has two, let's say, two branches here. For process 0, gather v is going to be called with MPI in place as the send buffer. And for the rest of the processes, it's going to be the send string. So, and then finally, after everything is over, these are like blocking calls, right? These collective communications are blocking collective communications. So this means that after this call returns, basically process 0 is safe to read the information from those receiving buffers. So all it does is just a simple code to print the results, the strings, and also the integers. And finally, since receive buffer and receive string are both dynamically allocated with malloc, you need to free that resources. Okay, so let's take a look at this example. MPI cc MPI gather v.c and MPI run. So you see that, again, the receive buffer, it gets all the information from the other processes, and it also gets all those C strings, which is a hello followed by the process rank. So this thing also works beautifully. And finally, we want to see how gather v, MPI gather v, works in inter-communicator scenario. The call involves all MPI processes in the inter-communicator, but with one group, as group A, defining the root. Again, the same drill, basically. All MPI processes in the other group B need to pass the value of the argument root as the root of the rank process, as the root of the root process in group A, and root passes MPI root for itself, and all the other processes in group A, which are in the same group as the root process of group A, they're going to pass in MPI proc null. This is the same drill as before, so I'm not going to spend more time on that. So this is going to be MPI gather v, the inter-communicator version. Everything else is the same. So you see, these examples are all in harmony. So we have always symmetry between the bare bone command, as I said. So we have MPI gather v, and then we have MPI gather v inter, which everything is the same, but you know, we have intra-communicator, inter-communicator, and that's the drill. So these are we're not going to comment on that. Again, same thing here, but note that displacements this time compared to MPI gather v is not going to be the size of the whole size of the communicator, because we want to work with intercommunicators. So that is why we have world size minus local size. So the displacements are going to be different, receive counts are going to be different, and we're going to, let's say, fill in the data. Again, displacements should be based on their rank, and receive counts, again, every process sort of in group B is gonna send one information to a root process of group A. Again, this is the root process of group A, which is responsible to allocate the proper space for the receive buffer. And again, the size is going to be the size of group B processes. So that is world size minus local size in my case. And finally, this is what we were talking about, that you need to be careful about this root thing that you're sending in this MPI gather v. Root is going to be MPI root for root process of group A. It's going to be 0, which is the rank of a root process in group A. This 0 is going to be used for all processes in group B, and all processes in group A other than the root process are going to send this MPI proc null. So again, we pass in all the required arguments, just like what the standard says. And finally, what we do is we just print the results. So these results are the results that the root process of group A is getting from all processes of group B. That is what the semantics mean in terms of MPI gather V when you're talking about inter-communicator. And also one very, very important difference is that we are not using MPI com world. We are using the inter-communicator between group A and group B. And we free the resources. Also, we free the local communicator and the inter-communicator. So MPI CC MPI gather V inter and MPI run. So again, gathered received buffer, this is a run with 8 processes. So this means that processes 4, 5, 6, 7 are in group B, and processes 0, 1, 2, and 3 are in group A. And this is root in group A. This is process 0 in group A, which says gathered received buffer from group B processes. And this is the received buffer that it gathered. Okay, so this is it. And these are examples that we don't care about them because we have our own examples. Let's continue our discussion. These are all examples. Okay, the next topic on the line is the scatter. Scatter is the sort of the reverse of the gather. So you remember that in gather, receive, buffer, count, type were only important at the root process. This is the reverse, so this means that the send buffer, send count, send type are going to be only significant at the root process, because the root process is the only process that wants to send information to all other processes in that communicator. Everything is the same as gather, but sort of the semantics are different. So I'm not going to spend time on this explaining all these stuff because I think at this point it's going to be a waste of time. So maybe we talk a little bit about the semantics. It says if the communicator is an intra-communicator, then the outcome is as if, again, this is not exactly what is happening, but you can imagine this in your mind as if the root executed n send operations, and each send operation basically moves or displaces depending on sort of the buffer count, or the buffer, let's say, location, that is the I, and then send count and the extent of that type that is being sent. And each MPI process in that communicator needs to also execute a receive sort of operation. And the send buffer is ignored for all non-root MPI processes. That is what we said, it is only significant at root process. The type signature associated with send type, send count, and send type at the root must be equal to the type signature associated with receive count and receive type at all MPI processes. This implies that the amount of data that is sent equal to the amount of data that is received pairwise between each MPI process and the root. So again, all these explanations are the same, so I'm not going to go over them. We have seen them in MPI gather and in MPI, like in intra version and in inter-communicator version. So in place again is valid. You can use it, and we're going to take a look at that example right now. So let's take a look at MPI scatter.c. Again, the example starts with an integer buffer and a C string style, C style string, again with 10 sort of characters. Rank 0 is the only rank that needs to take care of the send buffer, because rank 0 is the one that needs to send the information to all the other processes. This time around, after, let's say, allocation with malloc, then it needs to also preoccupy them with some data which are sort of unique, and it uses the iteration counter as the buffer, and then as the data, sorry, and then it prints the original data, and then it tries to basically allocate some strings. And this time, this %d doesn't represent the rank. It does represent only the counter of the loop. And then we print a sort of original data that the root has, and then we scatter it. And notice that we are passing here MPI comworld because this is the intra-communicator version. And then for the C style strings, we have different calls to MPI scatter. Rank 0 needs to basically call it with MPI in place. This time we don't put MPI in place in the send buffer, but we need to put it in the receive buffer. And then else, all the other processes need to send based on send string and this receive string. And you know that this send string and everything here is basically irrelevant. They're not significant, right? But anyways, because this is for all the other processes. And then rank number 0 is going to print the buffers, the integer and the strings. And all the other ranks also are going to print their information. And then finally, since the rank allocated that stuff with malloc, then it needs to free those resources. So MPI cc, MPI scatter. .c and MPI run. So here you see this is proc 0. It has all this information initially, these hello strings and these 0s through 7 because we have 8 processes involved. And then now after the scatter operation, you see that proc 0 or the root process has 0 and hello 0. And when proc 1 got its portion, it's portion from the integer buffer, which is 1, and its portion from the C string, which is hello 1, and all the way down to proc number 7. So this is how scatter works. Let's go back. Again, we need to consider the condition when we are working with inter-communicator. We have an example MPI scatter inter. I'm not going to talk about the semantics here because the semantics are exactly similar to what happens with, for example, inter-communicator at gather, but you need to reverse the explanation because in gather, only the root process receives the information from all the processes in group B, but here it means that only group B is gonna get the information from the root process of group A. So that's the only difference. So we're gonna take a look at MPI scatter inter-communicator version. Again, these things we're not gonna comment on that. Again, we are not working with CS style strings. We only work with integer. So send buffer is a null pointer, receive buffer. And then this is sort of local rank 0 and color 0. This means this is proc 0. I can write it also here. I think I forgot to add it here. This is proc 0 or root proc at group or in group A. So again, send buffer needs to be properly allocated. What's going to be the size? The size is not going to be the size of the whole processes, but it's going to be the size of processes in group B. The size of processes in group B is the word size minus the local size. Okay, so we have the mark of 23 minutes. I'm going to finish this example and then go to the next episode. So that's the proper size for the send buffer, which is allocated with malloc. And then we populated uniquely with some information. This information is not significant because it only uses the counter in the loop. And then we print sort of the original data at the root process. And then this is the drill that we were always talking about, that MPI root needs to be that element that we pass as root in proc 0 of group A. 0 is the root that all the processes in group B are sending, and all the processes in group A, which are not the root process, they need to send MPI proc null. And then we scatter the information with all those arguments, proper arguments. And then once we scattered the information from process 0 at group A, then all the processes at group B, they need to print the information that they have received. So let's go with MPI cc MPI scatter inter and MPI run. There we go. Now you see that the root process has the information 0, 1, 2, 3. That's the proper size. And these are processes 4, 5, and 6, and 7. When the size was 8, we already have seen this, that 4, 5, 6, and 7 are always in group B. So they get let's say, respectively, these elements, these integer elements of root process in group A. Perfect example. So I'm going to stop here and we're going to continue with the next episode.